Imagine this. You formulated your model, you wrote the code, you run it, and you wait to get your solution. You're checking the log, but things don't look exactly as you expected. Something has gone wrong somewhere. Sometimes you don't see much progress in the log. Sometimes you see that your model is infeasible. Sometimes you see warnings from the solver that something is not quite right with different numbers in the model. What is going on? Well, that's what we want to find out in this session. We are going to take a look at some of the most common issues you may face in your optimization models, what causes them, and how to address them. First, let's talk about the Big M. The Big M method is a technique where we use a large value, M, to help create logical relationships in mixed integer programming or MIP models. It's a very useful method in a lot of real-world applications to enforce specific behaviors based on binary conditions. For example, if we have a constraint that if y, a binary variable, is equal to 0, then x, a continuous variable, must be 0, then we can write it like this. Here, you see that if y is equal to 0, then x will be 0, and if y is equal to 1, then the value of x can take any value up to the large constant m. Where can this be used? Well, for example, there is a production or shipment amount from a facility, our variable x, and it can only happen if that facility is open, the binary variable y. Another example can be using Big M to activate or deactivate constraint. Look here. If our binary variable y is equal to 1, the first constraint is active, while the second one is inactive. Why? Because the right-hand side becomes small enough to make the constraint redundant. Similarly, when y is equal to 0, the second constraint is active, and the first one will have a large enough value on its right-hand side to make it inactive. Now you can see how the use of Big M allows us to control which constraints are active depending on the value of y. In both of these examples, the value of m should be large enough to avoid accidentally limiting the model, but there is a catch. While Big M is a powerful tool, one of the most common mistakes is using an excessively large value for m. The instinct is often to make m a huge number, thinking this ensures the constraints always hold. However, this can cause serious problems. First is numerical instability. Solvers are built to handle large-scale optimization problems, but they struggle when extremely large values relative to the other model coefficients are introduced. For example, if the largest of all the other constraints in the model is not even 100, but you use a Big M value of 10 to the power of 15, the solver will struggle to maintain precision across such a wide range, leading to rounding errors and inaccuracies. Second, using a large M leads to an increased solve time because it weakens the relaxation. So the solver has to search through a lot more nodes in the feasible space, which increases the runtime. Third, using an excessively large M can lead to incorrect results. Consider the example from the previous slide again. If here m is equal to the 10 to the power of 6 and the integrality tolerance of the solver is set to the default value of 10 to the negative 5, then this value of y, which is 0.00009999, is considered valid for a binary y because it satisfies a tolerance. As a result, x could take a value of 9.999 even though y is technically supposed to be 0. This completely contradicts the logic that x should only be non-zero when y is equal to 1. This is an example of trickle flow, where a continuous variable that's meant to be 0 when an associated binary variable is 0 instead takes a non-trivial value. In this example, we see that how choosing a large m can interact poorly with the solver's integrality tolerance. If m is too large compared to those tolerances, you could end up with non-integer solutions, or worse, a solution that violates your actual constraints. So what should we do? First of all, instead of giving m a grossly large value, use a value that's large enough so it still enforces the constraint. Next, use problem-specific values for m. Not every constraint needs the same m. Some constraints might need a larger m, while others can work with a much smaller value. For a given problem, use data-specific values for m. For example, you may decide that a value of 100 works well for your current dataset. But if you move to a much larger dataset and don't adjust that m accordingly, it could lead to incorrect results. But to avoid this, you shouldn't also opt for a value so large that it creates numerical problems. It's best to choose problem-specific and data-specific values. That said, this does not mean that you will spend a lot of time figuring out whether 870 is a better value for m or 900. No, it's more about avoiding unnecessary extremes. If you think 1000 is good enough, then use that. But don't use 10 to the power of 12 instead. That's where the problem arises. Finally, whenever possible, consider using indicator constraints instead of the big M. We have talked about them in Opti 201. Indicator constraints can directly activate or deactivate constraints based on binary variables without us introducing the big M. The constraints are easier to create because it's closer to how you think about a logical constraint. For example, like it says, if y is equal to 0, then x should be 0. Another advantage is that solvers like Gurobi may be able to leverage the implicit knowledge of what a constraint is doing and produce a tighter internal value of m than you might choose manually. This means that indicator constraints tend to be more numerically stable, though they may require additional processing time. Now, many people still prefer big M over indicator constraints when both are valid. But in my recent experiences, even when I think I've chosen a sufficiently small m, indicator constraints tend to take advantage of the model structure more effectively and give me faster results. So my recommendation is to start with indicator constraints if possible. Then, if the runtime becomes an issue and you suspect the indicator constraints are the culprit, then switch to the big M equivalent of those constraints and compare the performance. Since we've already mentioned numerical problems, let's now dive into them. So, what is this numerical instability? This refers to situations where the solver gives inconsistent or unexpected results or even struggles to converge. This is a very broad topic and we can't cover everything here. But overall, it can be caused by a few common issues. Rounding errors when building the model, limitations of floating point arithmetic, unrealistic expectations that we can have about the precision achievable, and the ill conditioning in the model due to geometry-related issues. We will briefly mention ill conditioning, but since this one is a bit more advanced for this series, we'll skip going too deep into it. But you can check the references if you'd like to learn more. Now, I want to say the last thing first. We will talk about some best practices to resolve the numerical issues, but overall, the best approach to improve performance is to reformulate your model. There are some parameters in the solver that can help, and we will talk about them, but there is only so much they can do, and they often come with a performance cost. So, with that in mind, let's begin. First thing to remember is that real numbers aren't represented perfectly by computers. Most software including Gurobi, relies on the double precision standards, which allows for around 16 significant decimal digits. That's quite precise and generally enough for most applications. However, a round of errors can still happen during arithmetic operations, especially when complex calculations or poorly scaled data is used. When data isn't scaled properly, or if the model encounters ill-conditioned matrices, which, by the way, those are the matrices where small changes in the input can lead to a large change in the output. In those cases, we start to see problems in the solution quality and consistency. So let's look at a simple example. If in Python you add 1 plus 10 to the power of negative 15 and compare it with 1, well, you get the expected results. It treats them as different, so you get false. But if you add 1 to 10 to the negative 16, suddenly they're considered equal. This should show that with very fine precision, values can blur together, making it hard to keep those differences straight in calculations. That's why it's crucial to ensure that your data is well scaled and precise. Without it, tiny inaccuracies in the data can cascade through the model and end up producing misleading results or numerical instabilities. Now keep in mind that poor scaling and imprecise inputs are neither necessary nor sufficient for numerical problems. But hopefully, the main takeaway is that proper scaling and precision significantly reduces the risk of numerical instability. So let's go over some practical recommendations for minimizing numerical issues. First, tighten the variable bounds using problem-specific information so that it reflects realistic values for each variable. Let's say you're dealing with a workforce scheduling model. In Gurobi, when you define the variables, by default the lower bound is 0 and the upper bound is infinity. But you know that the maximum number of hours an employee can work is 40 per week. If that's the case, then don't leave it as infinity. Setting that upper bound directly reduces unnecessary calculations and keeps the solution process efficient. Now, of course, this is a simple example, and in reality, the other constraints in the model cap the variable's value. But the point that I hope you take away is that if you know something that can help the model, especially with respect to the bounds, use them. Second, scale the data to avoid extreme values. When you're working with data that ranges widely in magnitude, scaling becomes crucial. Choosing appropriate units can really help here. So let's say you're dealing with some cost data. Do you really need to have billions of dollars for some coefficients and then cents and tiny fractions on the others? Just imagine yourself talking to some stakeholders and presenting some numbers on the slides. Which one of these numbers that you see here makes more sense in your case? Do you think anyone cares about this 609 at the end? Like, does it matter if you replace it with 3 zeros? Maybe in your case, even the 243,000 at the end is also redundant and everything should be measured in millions or even billions. If that's the case, then help the model. Rather than using individual dollars, shifting to thousands or millions make it easier for the solver to handle calculations without introducing numerical instability. Similarly, if you see a value like $0.0001, I think it's fair to assume that's 0, right? These tiny values don't impact the solution meaningfully, but they can cause issues in the processing. Next, try to avoid large big M values. We've already seen an example of this and how a large M value can lead to trickle flow. In Gurobi, there is a parameter called integrality focus. If your model has some numerical issues, setting this value to 1 may help because it asks the solver to work harder to try to avoid solutions that exploit integrality tolerances. However, it comes with a cost and the runtime goes up. But if needed, this is an option at your disposal. Next, try to avoid large multipliers in hierarchical objectives. Well, what does this mean? Let's say you're trying to optimize for several objectives and there is an inherent hierarchy between them. For example, you're optimizing for profit and then customer satisfaction. Now, sometimes the trick people use to model them is to aggregate these two objectives into one objective function, but with some large coefficients. So they use a large coefficient in this case for profit. If that's the case in your model, don't try to achieve it by assigning large values to the coefficients in the objective function. Instead, use the multi-objective optimization and set the customer satisfaction as your secondary objective. What does this mean here? This means that the solver first solves for profit as the objective and then uses that solution as a constraint while using customer satisfaction as the new objective. Finally, if you've tried all the previous recommendation and still faced numerical issues, then try different values of the numeric focus. This parameter controls how the solver handles numerical stability by balancing speed and accuracy. The default value is 0, which means the solver makes an automatic choice with a slight preference for speed. But if you are seeing persistent issues, increasing this setting to 1, 2, or even 3 can be very effective. Each higher setting shifts the solver's focus towards being more careful in numerical computation. But with higher values, Gurobi will spend more time checking the numerical accuracy and it will use more expensive techniques in order to avoid potential numerical issues. So approach this one cautiously. Gurobi also has some specific guidelines itself that can help manage numerical issues effectively. It's recommended that the matrix coefficients stay within 6 orders of magnitude. So ideally, they should fall within the range of 10 to the negative 3 to 10 to the power of 6. For the objective function, it's best to scale the values so that it falls within 10 to the 4. This can prevent the objective function from dominating or causing instability due to excessively large or small values. The same is also true for the variable bounds and the right-hand side values. However, the coefficients of the constraints are more important than all the rest. So pay closer attention to them. Well, let's see all of these warning signs in an example. This is a snippet from a Gurobi log. Here, you'll notice that the solver has flagged a warning. Model contains large matrix coefficient range. This message is a clear indicator of numerical instability. Here, it's suggesting that we might need to either reformulate the model or use the numeric focus parameter to handle potential numerical issues. On top of it, you see that the log is showing us the coefficient statistics that gives clues about the model's scaling. We see the range of matrix coefficient, objective values, bound, and the right-hand side. Here, the matrix range goes from 2 by 10 to the negative 6 to all the way to 10 to the 6. Remember the recommended range from the previous slide? That it says good to be within 6 orders of magnitude? But here, this one covers a huge span and probably a flag for instability. You can also see that there is a kappa value at the end. So what is this kappa? We briefly mentioned what are the ill-conditioned matrices, right? Those are the matrices where small change in data can lead to a large change in solutions. In Gurobi, we have kappa, which serves as a condition number. When kappa is high, it's another sign that the model may be ill-conditioned and prone to instability. And here, the large kappa hints at how sensitive the model is to numerical errors. So, in general, if you see warnings like this in your solver log, it's often a sign that you're dealing with numerical instability and that further investigation or reformulation may be needed. Now, let's talk about another common problem, and that's infeasibility. Infeasibility happens when no solution satisfies all constraints, and there are some common reasons for it. First, data issues. When we have inaccurate input data. For example, you have a minimum production quantity that's actually larger than the maximum allowed, or the weight of a package that you're shipping is more than the allowed weight limit. If you don't have any check in place or filters to catch these errors, they will find their way into your model, and then they can cause infeasibility. Next, simple coding errors. These can be things like accidentally defining variables wrong, making a mistake in how you index them, like, I don't know, writing xik rather than xijk. You might also set the bounds incorrectly or use an equality sign when it should have been a less than equality sign. This may seem very obvious to you now. Of course, if you have put something wrong in your model, you may get wrong results. But these trivial mistakes happen, and when you're deep into the code, your first instinct may not be to look at the simplest explanation, but rather something complicated. So one thing that I tell you right off the bat, resist that urge. Unless you already have a sense of what can cause infeasibility in your model, start simple and check for simple errors that might have happened in your code and the model. Finally, infeasibility happens when you have some conflicting constraints in the model, like the set of constraints that we see here, that clearly they are contradicting each other, because the sum of the first two variables and the sum of the second two variables both should be greater than equal to 1, but then it also says that the sum of all the variables should be equal to 1, right? So how should we go about finding and handling infeasibility? Well, one of the first things you can do to get to the root of infeasibility is to generate the .lp file of your model. This .lp file is the human-readable algebraic representation of your code that the solvers can provide. This file allows you to see exactly what's being passed to the solver and lets you check if there is any mismatch between what you meant to write and what the model is actually processing. Now, you can have a ton of variables and constraints, but that doesn't mean you need to go through every single one of them. Usually, the constraints are created through iterations. So quickly checking a few sample is usually enough to spot the issues. So let's see an example of this. Let's go back to the example we saw earlier, and let's add one extra constraint here just for the sake of illustration. So in this model, I only care about getting a feasible solution, so I'm setting the objective function to something trivial, like minimizing 0. Anyway, we run this, and we see that the model is infeasible, as expected. Checking the .lp file is as simple as using the right function on the model object and passing the name along with the suffix of the file. The LP file looked like what you see here on the right. I use the X as the name passed to the addVars function for creating my variables, and I only provided the name sum for the last constraint, right? But you can see them being reflected in the .lp file as well. I didn't provide any name for the first three constraints, so it just simply called them R0, R1, and R2. Now, of course, this is a very simple model, but in larger models, this exercise can be useful to ensure we didn't make any mistakes in the coding and in the model. For example, did I really mean to have the third constraint as less than equality? So let's continue with the same example and discuss another technique. Most commercial solvers have a feature that can identify conflicting constraints in an infeasible model. They do this by computing what's called an IIS, which is short for irreducible inconsistent subsystem, or if it's easier to remember, irreducible infeasible set. Essentially, an IIS is a subset of constraints and variable bounds that is infeasible on its own, but becomes feasible if any single constraint or bound is removed. Now, IIS may not be unique, and calculating it for large MIP models can be very resource intensive, but it's an incredibly powerful tool for narrowing down where the issues are. Back to our example. If rather than simply printing a message in the else part, saying the model is infeasible, we run Gurobi's compute IIS with just one line, the solver will tell us that constraints 0, 1, and the sum constraints together are causing the infeasibility. That means if you remove any one of them from the model, it becomes feasible again. Another effective way to manage or even prevent infeasibility is adding slack variables to your constraints and penalizing any violations in the objective function. This technique works especially well when you are dealing with a lot of constraints, making it hard to pinpoint exactly where conflicts are. By adding slack variables, essentially you're allowing the model to deviate a bit from the bounds set. So if we have a less than equality constraint, we add an artificial variable to the right-hand side, allowing the upper bound here to be a bit more. Of course, if you prefer, you can bring it to the left-hand side with a negative sign, right? Anyway, this variable is called a slack. If you have a greater than equality, you subtract the variable. For equality, you need both to allow the model to deviate in any direction. If it helps for you to remember that you can write an equality constraint by breaking it into a less than equality and a greater than equality. That means you need both variable with a positive sign and a negative sign. All right, let's look at our example again. For illustration, we added slack variables to all the constraints, and we added their sum, which you can see here as the sum of the violations, right? We could use different values for their weights, of course, if we have some violations that are more costly for us. Doing this, the solution tells us that S4 needs to be equal to 1, essentially saying by only violating the sum constraint by 1, we can make this model feasible. So the big advantage of this approach is that it transforms hard constraints into soft ones. This actually aligns better with the way most real-world problems work. For example, if you violate labor resource constraints, that could mean you need to hire temporary workers. Exceeding capacity constraints might mean renting additional space. Or if production constraints are violated, maybe outsourcing some production is an option. And minor violations like going over a time constraint could be acceptable to the business, especially if you can manage it by, I don't know, offering coupons or discounts to customers. This method, adding slacks, is especially beneficial in complex models or those with a lot of conditional constraints where stakeholders often provide strict rules that may not need to be quite as rigid as they first seem. Now, when you penalize the slack variables, you'll want to make sure the penalties are reasonably large, but not so big that they introduce numerical issues in the model. And keep an eye on the solver's log file to check the range of coefficients and spot any warnings about instability. You see, this is another full circle moment to the large big M values and the numerical issues that we've already talked about. If you have an infeasible model and relaxing some constraints is allowed, some solvers, like Gurobi, also have features that can help relax an infeasible model. You can then ask the solver to solve the relaxed model to get the solution. In Gurobi, you can achieve it by just using the model phys relax s function, which gives you some flexibility in terms of what can be relaxed and even the type of objectives to consider for the relaxation. All right, let's wrap up this part with some general tips to safeguard your optimization models from infeasibility. First, always start with the algebraic formulation of your model before jumping into the code. Now, this step helps you verify that the formulation is correct before anything gets too complicated. It also makes it much easier to share the model with others, whether that's a colleague, a support team, or even an online community when you need assistance. Second, make sure you have routines in place to check the accuracy of your data. Inaccurate or poorly formatted data is often a key source of infeasibility. So, catching issues early on can save you a lot of headache later. Finally, in many real-world problems, the stakeholders might provide rules as hard constraints, but in practice, they don't always need to be that rigid. Embracing slack variables is a great way to soften those constraints, which allows some flexibility and helps you avoid unnecessary infeasibilities. So be open to making some constraints more flexible when it makes sense. All right, now let's talk about something else that you should always pay attention to when solving your optimization models, and that's the solver's stopping criteria. Stopping criteria, as the name suggests, are conditions that determine when an optimization process should stop. Choosing the right stopping criteria is important because it lets you balance between solution quality and the time or the computational resources required. Two of the most common stopping criteria are optimality gap or MIP gap and the time limit. So let's start with the MIP gap. MIP gap controls when the solver can stop based on the difference or the gap between the lower and upper bounds of the objectives. This threshold lets the solver stop as soon as this gap is sufficiently small. In Gurobi, the default value is 10 to the negative 4. So here's the thing. There is a common misconception that if we set a higher MIP gap value, for example, like 1%, that means the solution is exactly 1% worse than the optimal. But that's not necessarily true. Often, the solver finds the optimal solution early on, but spends the remaining time proving that it's indeed optimal. Look at the plot here. The optimal solution is actually found, around 5 seconds time. But all the remaining time, Gurobi just tries to prove that it was in fact optimal. So, even with a 1% gap, you could be getting the optimal answer. It just hasn't been formally verified down to a smaller tolerance. To give a bit more context, and using epsilon for the MIP gap, that means that the solution you're getting is at most epsilon worse than the optimal. So for example, with a gap tolerance of 1%, you know that the solution is within 1% of the best possible outcome. But remember, as you set smaller and smaller gaps, the amount of work required grows exponentially, often for marginal improvements. Look at the plot here. Essentially, you're not getting much improvement after 1,000 seconds, and you are spending a lot of time for essentially nothing. That's why it's highly advised to set a positive MIP gap, especially in real-world application where model size and runtime constraints matter. I cannot stress this point enough, as I have seen more examples of this that I can count. I usually hear variations of this. You know what? You don't understand. Our problem is different, and we really need to have the optimal solution. Or, I don't know, I just want the best answer. So, what do? They put a MIP gap of 0 and then wonder why the model is suddenly running for hours rather than in a few minutes. So do this thought exercise in your team and involve your managers if you have to. Let's say you have a minimization objective and you have a crystal ball, and somehow that you know that the optimal solution is 100. Now, would you accept 100.01? If so, then you're already good with the Gurobi's default MIP gap, and you do not need to lower that number. Keep going. Are you okay with 100.1? How about 101? Go until someone brings up a good reason and rejects some further deterioration. I once had something similar with someone. Their objective function was in days, so like how long something takes. It turned out they were fine if the model comes back with 29 or 30. That's like more than 3% gap. This is an especially important exercise if you have multiple objectives, because it's no longer only one extreme or one best value that someone can compare with or, have a benchmark for themselves. You have multiple. And there are always trade-offs when you have multiple objectives. If you have two objectives, for example, and the value of one is 100 and the other is 30, are you okay accepting 101 and 29? And you can have different MIP gaps for different objectives. But again, since there are trade-offs in multiple objectives, and most people can't have a definitive answer on what they may compromise in one objective for a better value in another, what I've seen usually is setting higher values of MIP gap creates less of a dramatic response from the stakeholders. So now let's turn our focus to the other key criterion, which is the time limit. Here, you're simply setting a maximum time for the solver to run. The default is infinity, right? So the solver keeps running until it either finds the optimal solution within the MIP gap, or it hits another condition, or simply runs out of memory. Setting the time limit means if the solver hits the time limit, it stops and returns the best solution found so far, if any, along with a time limit status. If a time limit is like having a vertical line at one point in the plot, right? Like this one. So you can still see at that point what the gap is, and all the arguments that we had so far still holds. Setting a time limit lets you control when the solver stops, even if it hasn't reached the desired optimality gap. This can be especially important for those applications, maybe some real-time applications, when a solution should be reported within a specific time. Of course, setting MIP gap and time limit depends on the problem. If you're solving a strategic model that's run once a year but has a huge impact on the business, well, then maybe you better let it run for as long as needed, even if it is for days, to get to a desired gap. On the other hand, if you have an app where users expect to get results within seconds, if not shorter, maybe you care more about the time rather than the proven optimality. At the end, it depends on your specific application, but be sure to set both of them, even if your initial parameters are set to their defaults. Because depending on different data sets and the inputs you get from your stakeholders and all the scenario analysis that you're running, you can set non-default values as guardrails to ensure you hit the right balance between the quality and the computation resources. The main points that I wish to communicate are over. But since we're talking about modeling practical things, I thought to close it out with one more useful topic, and that's piecewise linear function. Piecewise linear functions come into play when relationships aren't easy to capture with a simple linear function. For example, consider the cost structure when ordering from a supplier. If you order up to a certain amount, let's say 3 units, the cost per unit is the standard cost, for example, $10 per unit. But if you order beyond that threshold, the supplier offers a discount, maybe $9 per unit for any units beyond the first 3. And if you reach an even larger quantity, the per unit cost drops again, $8 after you buy more than 10 units, right? In this case, we are dealing with a stepped cost function, where the cost changes at the specific points based on the volume. Another example might be bulk pricing for the entire order, where reaching a specific threshold lowers the cost of every unit ordered. So, if ordering 100 units costs $10 per unit, ordering 200 units could reduce the cost to $8 per unit for the entire batch. You've most likely seen both examples when shopping. Hey, buy 2 and the third one is 50% off. Or price of something is $5, but it's $4 if you buy 10 units or more. In both of these examples, piecewise linear functions can capture the relationships between different values and the tiers or breakpoints accurately. Another common use for piecewise linear functions is a linear approximation of nonlinear functions. Let's say we are modeling the sale of a product over a period of time, where the sale initially rises when the product is first launched, but then gradually declines as the market is saturated or newer products emerge. These often follow a nonlinear curve. Now, instead of solving a nonlinear problem, which can be computationally more intensive, we can use piecewise linear approximation. Basically, we break the curve into smaller linear segments, each capturing part of that relationship. This approximation allows us to retain much of the accuracy of the original curve while keeping the model simpler and faster to solve. In Gurobi, if you want to write a piecewise linear constraint, it's as simple as providing the 2 variables that you're building the relationship for, and then giving the breakpoints associated with those variables. Gurobi will take care of the rest. Of course, using piecewise linear functions as an approximation has its pros and cons. On the pro side, piecewise linear approximations simplify complex nonlinear relationships into manageable segments. So, instead of dealing with full nonlinear equations, we get a close approximations that many solvers handle more efficiently. This is particularly valuable when you are working with nonlinear relationships that might be too complex or not even possible using the solver's supported nonlinear functions. Now, on the downside, approximating highly nonlinear curves with piecewise linear functions means sacrificing some accuracy. When we have sharp curves or intricate shapes where capturing a small list of the details matter, then linear segments may struggle and not be as precise as a true nonlinear approach. There's also a bit of a gray area to consider. Adding more segments can give you a more accurate approximation, but also it increases the model's complexity and runtime. This is especially true if you're working with a model that already has a lot of segments or where a high degree of accuracy is essential. To manage this, and if possible, it's often worth trying both approaches. Modeling the nonlinear functions directly, which is now supported in Gurobi 12, and also using a piecewise linear approximation. By experimenting, you can see which method strikes the best balance between performance and precision for your specific problem. We are only scratching the surface here, and you will learn more about nonlinear functions in other sessions. Well, that's it, folks. We talked about some real-world challenges that you're likely to encounter when working with mathematical optimization models and how to tackle them effectively. We walked through the intricacies of the Big M method, how to handle numerical issues that can sneak up in the model if you're not careful, managing infeasibility, and setting stopping criteria as a practical way to control resource consumption. I hope you have picked up something new today and feel better prepared to handle these challenges when they come up in your projects. Thank you and happy modeling.